Thank you very much. My name is Martin Roa-Villescas. I'm a PhD candidate of the Eindhoven University of Technology. I will be talking about TensorInference.jl, which is a package for probabilistic inference using contraction of tensor networks. I've been working on this together with Jingguo Liu, professor at the Hong Kong University of Science and Technology of Guangzhou, and also together with his student Xuanzhao Gao, and together with my supervisors Sander and Henk, and then this is me. So this is a collaboration between the TUE and the Hong Kong University. So this is the outline. First, I'm going to motivate why we are interested, at least in the research groups I've been involved in model-based machine learning. And I'm going to very quickly walk you through what it means to do probabilistic inference. And then I will introduce the package TensorInference.jl. We'll start with an example. Then I'll tell you a little bit more about the inner workings of the package. And finally, I will show you some performance benchmark, comparing it with other libraries, and then some concluding remarks. So, model-based machine learning. So there is a very interesting parallel between the way that animal intelligence has evolved compared with the way that AI is evolving. So if we go back 600 million years ago, we had the first animals that were out there were sponges, jellyfish, flatworms, and they were really about instincts, yeah, about stimuli and response. And they started evolving into fish, amphibians, reptiles, but they got complex, but not smarter. So there would be like more layers of complexity, but not smarter. However, 100 million years ago, we started seeing primates and whales, dolphins, and humans after. And then in that moment, actually, there was a real change in the architecture of the brain. And neuroscientists have seen these differences in the brains. The old brain is great, by the way. You know, these animals survive in the wild, and they are really good at hunting and surviving, but it has its limitations, so it's good to talk about them. For example, the old brain requires really a lot of training data in order to achieve what they can do. And it generalizes very poorly. It has no model of the world, so there is this illusion of intelligence. For example, this frog has a circuit in his head. When he sees pixels that resemble a bug, he will just try to eat it. No matter how many times he sees that, and he won't learn quickly. He'll just keep trying to eat those bugs and maybe starve to death, right? However, whales, mammals who have similar brain like we humans do, there's a very nice story about this one. So the trainers reward the whales whenever they pick up trash from the pool. One time, a seagull died. It picked it up, and it took it to the trainer, and it gave it several fish because he took a big object. So what the whale started doing was using some of the fish it received to get some more seagulls and get more fish in return. So that's already some kind of difference in the intelligence, right? So, by the way, the new brain requires less training data, generalizes better. So if you move it to a new complete environment, it generalizes better, and it learns a model of the world. So that's why we think that model-based learning is the way to go. By the way, we still have the old brain. Yeah, and it takes care of things like keeping the control of the temperature of your body, or the blood pressure, the immune system, the nervous system. But this is the neocortex, and this is the stuff that grew on top of it. And that's the part of the brain that helps us to plan, to all the cognitive kind of reasoning that we have. So basically, model-based model-free supervised learning dominates AI today, so like using neural networks. But we are interested in model-based supervised learning. Why? Because it allows us to incorporate background knowledge into the learning process, and therefore we need less data, we improve the robustness, and we can explain why our models make the decisions they do. So basically, that's the motivation. And how am I going to help on this mission? Well, I'm going to compile models with background knowledge using tensor networks. And I'm going to perform inference using the state-of-the-art tensor technology. Tensor networks come from the physics domain. It turns out that they have done amazing, amazing advances in the efficiency with how these tensor networks perform. And my idea, and by the way, these tensor networks are largely used in neural networks as well. So my main goal is taking some of the nice stuff they have done there and bridging it with the model-based machine learning. Okay, so crash course on probabilistic models or on probabilistic machine learning. So a probabilistic model consists of a set of random variables. A, B, C, and so on, and a probability distribution. This is called the joint probability distribution. And how do we represent this? Well, every single configuration of the system, so the combination of the values of these random variables, has assigned a probability. Yeah? And then in a probabilistic model, if you add all the probabilities here, they should add up to 1, right? That's probability theory. However, in the field or in the branch of machine learning that I'm working with, this is not very important that this number should add up to 1. So I'm going to relax this constraint. I'm just going to, hey, you know what? That's a function, and it's just basically a function of some variables, k, j, i, and it is, and each possible configuration is associated with a value. Yeah. But there's an issue. There's an issue with this function. It's like every time you increase a variable, so every time you add a variable to the system, the state space, or the state space duplicates. So there's an exponential growth, right? So basically, if we have a model that has 200 variables, we will have this number of configurations. And this number cannot be even represented natively in a computer. So we need to solve that. How do we solve that? By the way, yeah, real models have way more than 200 variables, so we definitely need to solve this. One way of solving it, so the first step to solve this is like, hey, we can factorize that function that represents our system. And that already, it's a way of data compression. You need way less values to represent your overall system, right? So you have more tables, but with less values. And overall, you need less configurations, less values to store the model in your system. And by the way, we scientists and engineers, and I was talking about that earlier, we love representing things graphically. So that factorization that you see there is what we like to represent with graphical models. This is called a factor graph, where the variables are the edges, and the factors are the nodes. So for example, f is a function of j and I, as you see the factor there, and so on. This is a factor graph, and there's more. There's Bayesian networks, Markov random fields, there's tensor networks, which are pretty much similar to this ones. So here we go. So what is probabilistic inference? Well, probabilistic inference is the process of evaluating this formula, which is basically you want to find the probability of one or a subset of the variables of your model. That means that you have to sum out or marginalize, is the term that they use in machine learning. They use contract in the quantum world, the tensor networks. And then you want to contract or marginalize all the variables that you are not interested in. So in this case, we're interested in a function that is only a function of IKL, so we have to marginalize J. So one way to proceed is like, hey, you know what? Let's just multiply all those factors, and then we just sum out J. But hey, this is a naive solution. Why? Because then we're going to the previous problem, where this table is going to be huge. Suppose that we have many, many variables. This table is not going to be feasible to represent in a computer. So therefore, what we do, and it's called an algorithm called variable elimination, we're going to push in those summations as far as possible. And then here the largest factor is going to be over 4 variables, and here the largest factor that occurs is going to be over 3 variables. And remember, a variable difference, we're talking about exponential changes. So it does make a very big difference. And the key property of why this is useful is it can be summarized in this equation, the distributive property of multiplication over addition. The left involves 3 operations. The right involves 2 operations. If you first perform the addition of b plus c and then multiply by a, then that's only 2 operations. So this is basically what's happening, why it's useful to push in those summations. I'm not going to go too much into detail here, but this is basically how you multiply these discrete models that I'm working with. I'm not working with continuous variable, only discrete variables, and this is how you add. So basically, those are the 2 operations that we do, but we need to do them very efficiently in order to handle very big models, and that's where I'm going to later. However, we still have a problem. Look, in big model, we're going to have very large models with a lot of variables that we need to marginalize or to contract. So the question is, in what order should we do this? And that problem is NP hard. Deciding what order should you marginalize to push in those summation and perform the summation and then continue with the other one, with the next one, that's NP hard. And that's what we're trying to solve. So probabilistic inference is NP hard. So let me tell you about TensorInference.jl. That's the package that I've been building mainly with Jingo. And it relies on einsum.jl. which is a tensor network infrastructure that our package builds upon. It has gradient computation via differentiable programming, and basically it's using state-of-the-art algorithms to perform the type of operations that we saw earlier in the previous slide. It also uses generic and tropical tensor networks, which has turned out to be very useful because we managed to solve different types of inference tasks just by changing the type of the elements of the matrices. So for example, if we use tropical elements and the related tropical algebra, we can solve different kind of problems, and I will show you what I mean with that later. And also, we are using the hyper-optimized contraction order finding algorithms which have been developed in the quantum field, which are very, very superior to compared to the stuff that at least I found in the Bayesian machine learning toolboxes that I've experienced with. These hyper-optimized contraction algorithms include this local search method, some min-cut methods, and a greedy method. And finally, this tensor network-based infrastructures makes great use of the BLAST routines and GPU technology, which also allowed us to improve quite a lot the performance compared to other packages. So what are the kind of things we want to solve? So this is a series of 4 tasks that we solve using our package. The first one is called the partition function, or the probability of evidence. It's basically just summing out every single variable of your model. And the end is going to be just a scalar value, and that scalar value has different purposes depending on the application. The other one is called the marginal distributions over all variables given evidence. So for every single variable, we're going to marginalize the rest. Yeah, so we know, so suppose we have a very complex model in the medical domain, and one of the variables means like, hey, the patient has cancer or not, and we want to know what's the probability that the patient has cancer. So you have to marginalize all of the other variables except that one in order to know that probability. And we do that for every single variable of the model. The MPE stands for the most probable explanation, and it's the most likely assignment for your system. So basically, which is the configuration that is most likely. Here we use, instead of summing out things, we use the max or the maximum operator. And finally, mmap, which is a combination of the previous 2 tasks, which is you first marginalize some of the variables, and then you find the most probable explanation for the remaining ones, right? So these are by the way, these tasks come from the UAI inference competition. Every, I don't know, 4 or 5 years, there's a inference competition in the UAI conference. It's called Uncertainty of Artificial Intelligence Conference. And then these are the exact same inference tasks that they solve there. Finally, we also offer the option to sample the posterior distribution given some evidence. By the way, all of these tasks are in the context of evidence. So if you have observations for any of the variables of your model, you can always plug them in. So all of these tasks are like given some evidence. Let's look at an example of this is a very typical example, educational example present in many books. It's called the Asia network. It has 8 binary random variables. The first one says whether the patient has been to Asia, recently been to Asia, and the last one says whether the patient is suffering from dyspnea. And there's a few more variables. And now this comes from the knowledge of the domain. So for example, here we have, this is a Bayesian network, by the way, and we have that the probability that the patient has lung cancer is conditionally dependent on whether the patient smokes. So this is how you would build this graphical model. And remember, all this is showing is how does the joint distribution factorizes. So this is just a representation of the factorization. And then let's suppose we have observations for variables A and D. So we know that the patient has been to Asia, and we know that the patient is suffering from dyspnea. So you load the package, you read the model. It's this asia.ui is just a file in which the model is defined using the UAI format. You can find information about that in our documentation package, but also in the UAI inference competition. And here we're creating the tensor model with the data from the loaded model, and we're saying, and we're feeding in the evidence saying like, hey, variable 1 and 8, they are both true, or they're both 1. So it creates it. It gives you some information about the contraction time, the space complexity, and the read-or-write complexity. This is how you calculate the partition function, by the way. So in this case, it's 0.55. In Bayesian machine learning, this partition function can be very useful to compare the accuracy of the models. So you can compare models using this partition function. Marginals, so in this case, we can find the marginal probability for each of the variables in the model. So basically 8 and 1, variable 1 and 8 is 1 because we said it was 1, but then it finds the probability of the rest of the variables. Here is asking for the most probable configuration, but it doesn't only give you the most probable configuration, which is in this case is that all variables are 1, and it also gives you the associated probability. And then here we're saying like, hey, we want to know the most probable configuration for variables 4 and 7, given this evidence, and then please marginalize the rest, and then we get the answer. Finally, we can also sample our distribution, so you're just sampling from the joint distribution. How does this work, and how do we achieve remarkable inference? So this part is the more interesting part. So this is the kind of equations that this is the kind of formula that needs to evaluate it many times in an application. So we need to make sure that this is done extremely efficiently, and it's just a product of factors, and then we sum out some of its variables. So the first step is that we find an optimal pairwise contraction order of the input factors for minimal memory use. I'll explain that more in detail in the next slide. And after one, we formulate each pairwise factor contraction as a batched general matrix multiply. And this is also helping a lot in our performance. So what does it mean to find the optimal pairwise contraction order? So let's simplify this equation. Let's just say that we have A, B, C, D, E, F as factors. So it's coming up with a schedule like this, like, hey, first you need to multiply F and D, and then you store it on an intermediate result. You store it in 1, then you contract it with B, and so on. So how do we and the question is, how do we come up with this order using this algorithm? Basically, it's just we are just finding step by step the 2 factors that produce the result with minimal space complexity, and that's what the memory cost function does. Finally, we run this several times until there's only one tensor in our list, and then at that moment we have something like this. Yeah. So this minimizes the largest factor or the largest tensor that appears anywhere in your computations, anywhere in your intermediate computation. The second step is like, hey, batch gems. Batch gem stands for multiplication of matrices in batches. So basically, you have one batch here, you have one batch here, and you multiply them, and it's done very efficiently. So the trick that we have is that we're going to, so here we have like arbitrary indices, and when we contract them or when we multiply them and sum out some of them, we get a result. However, we need to reshape these tensors in order to meet the format that is expected by the gem. So basically, this involves a lot of permutations and grouping of indices. Then we perform the operation, and then we go back again by permuting and grouping indices into the format that operation should result in. Yeah, so that's basically the second one. And what are the benefits of these batch gems? So the batch general multiply, they are vectorized operations, so you're performing many operations at the same time. They have low-level hardware-specific optimizations. They amortize the overhead through doing this in batches, and both NVIDIA and Intel provide really highly optimized implementations. So that's also one of the sources where we're getting the very good performance from. So let's look at the performance benchmark. So here we have, so what I'm going to show is a naive backend I had 2 years ago, compared with the tensor-based backend that we implemented using one more axioms.jl. And what I'm going to show you is the speed up, which means like whether the new tensor is faster, whether the new backend is faster or slower. And I'm going to change 2 parameters. I'm going to change the dimensionality of the tensors, or the rank of the tensors, and I'm also going to change the number of factors involved in this equation. Yeah, so this is what you see here. So what we can observe here is like for low dimensional tensors and low number of factors, we have slowdowns. By the way, red means big speed up, blue means slow down, white means, hey, same time. Yeah. So what we notice is that as the dimension grows and as the factor increases, we get more and more performance, which is nice because we are actually interested in very complex models, which are the ones that occur in real life. Why do we get slowdowns here? Well, there's an overhead, the penalty that we pay for doing all the tricks that I showed you in the earlier slide. So therefore, we are slow when there's not enough calculations to compensate. So this is also already really good. By the way, this was just for one equation comparing the old backend with the new backend, with the tensor-based backend. But here, this one shows a comparison between our library and other libraries. In this case, libdi, Merlin, they're coded in C++, and junctiontrees.jl, which is a package I wrote 2 years ago, and we could say it's like the predecessor of this TensorInference.jl library. So what we note here, again, is like, by the way, let me explain what each point means. It's, again, a speed up. So if the point is above 1, then we have a speed up. If the point is below 1, then we have a slowdown. So we can notice that, by the way, note that the y-axis is in logarithmic scale, which means that we are basically achieving some kind of like exponential improvement when the space complexity or when the complexity of the problem grows. Yeah, thanks to the 2 tricks I showed earlier, which is something that we were super happy to see. And these are, each graph corresponds to the different tasks. The trend is quite similar. In this one, we had to use a different benchmark because not all the libraries supported this task, and the original benchmark, that one was meant for approximate algorithms, not for exact algorithms, which is what I am focusing in. And we also integrate the GPU, and indeed, we also noticed that the space complexity has to be quite high in order to achieve speed as with the space complexity. Otherwise, we will have slowdowns. Concluding remarks. The ecosystem is growing in the Bayesian inference community in the Julia context. TensorInference.jl is very nice to when your models have discrete variables. JunctionTrees.jl is basically deprecated since we have TensorInference.jl, that's my old package. RxInfer.jl, also a package developed in the Eindhoven University of Technology by the Bias Lab group. It is excellent for real-time performance, mainly for continuous variables, mainly for continuous variables. And it uses like a reactive paradigm, which is also very interesting. Turing.jl is really nice because it's very universal. It uses sampling methods or stochastic sampling methods to compute the posterior probabilities. So probably some models, so probably that's one of the drawbacks of RxInfer.jl, that is not as universal as Turing.jl, but when the model is compatible from RxInfer.jl, then you probably get much better performance. And it supports real time, which I'm not sure whether Turing.jl does. Gent.jl, to be honest, this one, I just found out about this one recently, and I saw it has a lot of stars in GitHub, so I'm definitely going to look into this library. I think it was developed in the MIT, so I'm curious about it. Looks pretty good. The summary. TensorInference.jl, a Julia package for tensor-based inference in discrete models, scales well with model complexity, supports the most common probabilistic inference task in this discrete domain. It has GPU support, and it's already being employed for quantum error correction, so don't miss the talk. The package is called Tensor Quantum Error Correction, and it's going to be presented tomorrow. So if you're interested in these topics, make sure you don't miss it. Conclusion, hey, tensor technologies can lead to significant performance improvement. I am glad that we are helping to bridge all the very nice work that the physicists have done in the quantum computing domain and trying to get those very nice results and reuse them in the Bayesian learning community. Here's the URL if you're interested in the package. Please go and visit, maybe open an issue or start using it and let us know what you think. And we've already published a few papers related to this package. So if you want to go more into the details of how this is exactly done, you can look at this one. Yeah, thank you very much.
Questions?
Hi, thanks for the nice talk. Do you have any kind of thoughts on, presumably there are factor graphs that you generate, say like one that looks like a square lattice, that are too hard to find an optimal contraction, or to even find a good contracting order, and then let alone contract the whole thing down. Do you have any thoughts on like what happens with the package in that case if I just give it a probability model that's just too complicated?
Yeah. So so the key thing here is we're doing exact inference. And that means that there are some models will just become too difficult to do in an exact manner. And that is determined by, in general terms, is determined by the tree width of the factor graph that we're talking about, right? If it just results in too big to compute the exact way, that's the moment where you should really go for the approximate versions. And there's variational inference for that purpose, and there's also the sampling methods, right? Like Monte Carlo methods. So the question would be, is like, what is the tree width of the factor graph that we're talking about? If it's under, I don't know, like a tree width of under 30, I think our method will be able to deal with it, and you will get exact results. So that's one of the issues with the approximate versions, that there is no guarantee that the posterior distribution that you're inferring is the correct one. Sometimes these sampling methods or even the variational inference methods, they just give you really wrong results, but in some cases, for some models, yeah.
So I think it's been kind of half answered, but you are focused on exact contraction. Is approximation supported in this package as well nonetheless, or is that like something where I should go a different package then?
Yeah, good question. We're only doing exact inference so far. There is actually a pretty straightforward way to create approximate versions of this. We could actually create a threshold for the different values, and if they're below a certain threshold, you can actually just make those probabilities go to 0. And that already also creates more sparsity in our tensors, and then you could do approximate versions of this. But that's something that is not on our package yet. It might be like something we might implement in the future. Yeah.
We have one more question, and I think we should go to and stop.
Yeah, thanks a lot for your talk. The question is basically about the model construction. Do you always use you showed the example from UI, but is there like an API or like function call how to construct these graphs within the package?
Good question. Yeah. So indeed, like our focus in our research has been that these models are given to us, right? But there's a huge loads of theory of how to learn these models from data. Sometimes you just can learn them from statistics. For example, we can see like what is the statistics that somebody has a given disease, right? So you can read that from the medical domain. But if you have a lot of data, there's also a lot of theory that explains how you can come up with these graphical models based on that existing data. And there is a very good book on Darwich. He has several chapters devoted on how to learn these models, right? What I focused on is just, hey, we have the model and we need to perform fast inference.
Yeah, it was a great talk. Thank you, Martin. And I think that I was really inspired. I will try to steal something for TensorInference.jl. So round of applause for our speaker.
Thank you very much. Thank you.